Today we are going to discuss a paper of Henry Moseley from 1913. That was the British Royal Society. And it was communicated by Professor Rutherford. Why? Because I think in that year Henry Moseley was in the army of the British Army. I think he died a year later in World War I. It was received on April 22nd, 1913, and it was read or published May 1st, 1913 from the University of Manchester, England. And the title of the paper, The Attainment of High Potentials by the Use of Radium. Simply, is trying to measure the voltage that was produced by the radiation of beta particles from the radioactive element of radium. At that time, the beta rays were already identified as negatively charged particles emitted from radioactive material like radium, and nobody knew how high the voltage is. Let us see how Henry Moseley was able to make an experiment to determine the voltage or the amount of energy loaded on the beta particle. So the work was to measure the energy and the numerical importance of the beta particles. As we said, beta particles are negatively charged particles or electrons. And the experiment is to calculate the energy of the beta particle. It will turn out to be that the beta particles are very energetic particles. And they are negative because they are deflected in a magnetic field like electrons. At that time, to measure the energy, you have to use a gradient of positive charge, slow down the electron to have any idea about their energy and the distribution of the particle. Another way, that is a source of radium that radiates beta particles. That is the radium, or the active material. And the beta particles are emitted from it. So what you do is to use an ionization chamber, or to measure, this is a chamber that's going to measure the beta particles going through the ionization chamber, and that would be, you will have a gauge that tell you how much charge is received by the detector. So what you do, you come in the middle here, you put a positive charge to slow down the beta particles that are going through the detector. By increasing the positive charge, you can slow down the electron or cut them down almost to zero, assuming that you have sufficient potential between the source and the screen. That is your potential. If you have sufficient voltage, you can resist the beta particles from passing this barrier. The problem at that time, there was no enough voltage, positive voltage, to do that. You need millions of voltage to do that. So theoretically, both the energy and the distribution of alpha particles could be measured directly by giving gradually increasing positive charge. That is theoretical. Practically, for when the potential of the source is positive, P positive electrons processing energy less than any electrons that have energy less than E, which is the electric charge, times V, will be drawn back or stopped to the source. So another way, you will have a source that emitting, as we said, beta particles, and you are going to stop it you are going to use a screen and putting a volt on it, and the emission, those are the electrons that are negatively charged, and you are going to use a positive volt. The electrons that can go through that screen, you will have two forces now. A force of E, that's the positive, that will That's the charge you put on that screen. Caused by the force, the voltage that of E that you try to figure out. So this voltage is unknown. You try to figure out the voltage of energy carried by the beta particles by your own volt that you put on the screen when you have an ionization chamber here to measure how much current can go through it. This is the current measurement. Any electron go here will generate a current in your meter. That is the experiment of Henry Moseley of 1923. The problem here, unfortunately, more than 1,000,000 volts would be necessary to stop the fastest beta particles. This is the whole purpose of the purpose is how to measure the energy of beta particles when you don't or you cannot generate millions of voltage. So the author said no method in the present is at present known of maintaining such high voltage in vacuum. You cannot generate 1,000,000 volt in vacuum without having to have discharge or ionization. It was thought that this difficulty might possibly be overcome by using the active material itself, which is the radium. Your active material is the radium. In order to produce high potential according to the principle employed in Strutt's radium clock. So there was an experiment that was done by Strutt, and that is the publication, the Philosophical Magazine of 1903, the volume 6, page 66. What does the principle involve? The potential using the active material to generate enormous voltage that you cannot generate it in the laboratory in vacuum. How do you do it? If the source of radiation were perfectly insulated, the problem here, or the issue here, how to insulate the source of radiation. Its potential would rise until the swiftest beta particles could no longer escape. Another way, Mosley is going to do what Strutt did, getting the radium insulated in a capsule or glass capsule that is thick enough, the wall of the capsule is thick enough to prevent beta particles from escaping. The present note, or this paper that we are discussing, deals with experiments made to test whether this method was practicable. It was found that the conclusion of the experiment we are going to discuss now, that high potentials were readily obtained, but the attempt to attain 1,000,000 volt failed. Why can't you generate 1,000,000 volt? Because your material that you are using to insulate the radiation in the capsule will break down, failed through the difficulties of insulation encountered. So the whole problem here is how to insulate the high voltage in vacuum. But few experiments were completed and many failed as a result of accidents. This shows that even if perseverance had been rewarded by greater successes, technical difficulties accentuated every effort to improve the insulation, would probably have prevented the practical application of the method. It seemed therefore useless to pursue the matter further until more is known of the reason why the insulation of a vacuum breaks down. Another way, Mosley is going to do the experiment and he is going to discuss why insulation in vacuum is impossible at certain voltage. The experiment is a beautiful experiment, took a lot of work. Here's what he did. He put that small point B is a ball, a glass ball, about 1 centimeter in diameter. He is going to put the radium inside that ball. That is a gas he is going to put inside. So that is B. B is that little ball inside this one, this ball right. That glass ball is manufactured in the university by the glass blower of the university. It has 1 centimeter diameter, and he also going to go through a 9 millimeter diameter that's going to break down Then he is going to go through the 5 centimeter diameter. He is going to do 3 experiments with that little ball that has radium inside. That ball is surrounded by the flask F. F is the flask. F is this entire container that has 1 liter volume, including the entire connection to it. So what is the flask does? The flask is evacuated from air, and he is going to generate a capacitor. The capacitor will be when the particles inside B generate alpha particles, they cannot escape from this ball. This ball right here is going to keep the beta particles, the electron, inside this ball. So why do you need the flask? The ball will be negative charges inside it. It's going to insulate it. Because you have negative charges, they are going to generate positive charges in the side of the flask. It's like a capacitor. And you are going to have negative charges outside the flask. The flask is neutral. So let us repeat again what the experiment does. The experiment is that you insulate the radiation inside B. That is little ball. And you evacuate. This is your vacuum pump right here. The pump will suck the air from all these tubes, and he is going to use a charcoal here to suck the water and any impurities, charcoal in E and C. And he is going to use the tube D to measure the vacuum, how much vacuum he got. And he is going to discuss the bypass P. That is a technical trick he is going to use to seal the tube, and the T is the stopper that's going to seal the vacuum. And the other 2 components of the experiment are the long rod that is used to insulate the sphere from the flask, and another long spring of silica. This is long spring. This is going to be used as a spring. When it bends up and down, it will indicate how much force you have on that plate. E is a metal plate suspended from a spring. So that spring can go up and down. When there is a force that pulls the aluminum down, will push it up. Where does the force come from? The force comes from generating a negative charge by the electron on this pole. It will generate positive charges on the plates, and will pull the plate downward, and the force will be E square, Coulomb's force, E square divided by R square. This is the force of attraction. This is Coulomb's force. You can put some constants here. From that force, you can calculate the energy, which is E, phi E was minus, and the V is the unknown that you try to figure out. This is your force. This is your potential times the charge will get you the force, and that is the force you're trying. In describing the experiment, the beta radiation source was a purified radium emanation or radiation that has about 20 millicurie. So it was calibrated 20 millicurie of gas or material of radium that will put inside the B tube or the B pulp contained in a thin pulp. The pulp has 1 centimeter in radius, as we said. This is P in the figure. The diameter of the pulp P that has the radius. The bulb was thick enough to stop all alpha radiation. Are we talking about alpha or beta? Well, alpha radiation is not going to escape. Beta radiation cannot escape either. The bulb B was supported on a fine thin silica rod R. That is R. That is the rod R that supports the bulb that has the radium. Why is he talking about alpha particles, radiation? assuming that the radium is going to radiate alpha and beta. Alpha is the helium, and the beta are the electron. By a fine silica rod are inside an exhausted glass flask. F is 1 liter in capacity. F is this flask that contains a smaller thin pulp. The rod of a diameter about 0.8 millimeter was freshly drawn from fused silica, transparent glass. The surface of the pulp and the flask, this is the most important portion, very creative. The surface of the pulp and the flask was coated by silver. Why silver? Because it is metal. He wants to have a conductive surface, so he used silver. He heated the silver, it was coated by silver, which was found to retain trace of conductivity when subsequently heated to 400 degrees centigrade. When you heat it, it becomes transparent. Another way, you can still see through the glass. So that surface was coated by silver, and the other surface of the bowl was coated. So you have surface of the bowl of the bulb was coated by silver, and the surface of the glass of the flask was coated by silver. That make them conductive, which make them able to conductive, which make them able to induce electric fields and separated charges on the surface, but you still need the insulation between the two surfaces in order to create a capacitor condenser. So that is the silver part, the silver covering to create a conductor. The potential gained by the bulb was measured by a simple form of attracted disk electrometer. The electrometer is the electrometer, or a disk, aluminum disk, suspended on a spring of silica. When it is attracted to the ball by the induction of a charge. The induction will happen because the beta particles will generate negative charge on the bulb. By induction, it will generate positive charge on the next surfaces. The aluminum disc that has 1 centimeter diameter will be charged positively and will be attracted. And from the bending of the alumina of the silica spring, that long spring suspended or soldered with aluminum side of the flask, the bending of that spring due to the attraction of the aluminum disc will determine or indicate the amount of force imparted on the aluminum disc. That is the portion of the disc electrometer. Circular aluminum disc being hung from the arm of a horizontal silica spring, the other end of which is soldered with aluminum to the projection from one side of the glass of the wall of the flask. By observing with a microscope, this is another necessity of the experiment, because the deflection of the silica spring is going to be small. The displacement of the disc, the force of attraction exerted on it by the bulb was measured. By measuring the force, the displacement of the disc on the silica, and from this it was easy to calculate the charge and the potential acquired by the bulb. The entire experiment is to measure how much electric voltage or potential is produced on the glass pulp by the beta particle. The force of a dyne displaced the spring by about 0.1 millimeter. How small that? So you need one dyne to produce this kind of force. How did he figure that out? Most probably he did other side experiments that he did not describe here, because this is a note. This paper is a note. It's not a fully detailed article. The disc was hung just at the entrance of the mouth of the flask, so the remainder of the flask wall served the purpose of a guard ring. Guard ring means created a capacitor. Just do it again from here. So the disc of the electrometer is the mouth of the flask. This is the mouth of the flask right here. And this entire flask will act like a guard ring. Ring means surrounding a negative source, you guard it, which means all the electric field that is radiating outside will generate a positive charge on the silver of the flask. Opposite side, because it is neutral, it will have to be negative. So why do you need the flask? You need the flask because you are going to evacuate very deep exhaustion of the system. Avoid having any air in this area around the radiation. If you have any air in this area, you're going to have a spark or discharge. If you have discharge, you cannot measure the voltage of the bulb. So the rest of the experiment is going to describe the very painful effort of evacuation of the flask. How did Moseley achieve deep vacuum in the system? In this paragraph, the author discusses the technique he used to achieve extreme vacuum to avoid any spark in the system. The purpose of the vacuum was to remove the gas and the water vapor and any particles such that spark or discharge do not occur, and the electrons will stay on the surface of the bulb that contains the radium and the surface of the flask that contains the bulb. Here the author discusses how he measured the residual volume. The residual pressure of the gas cannot be measured by any gauge or a mechanical indicator because we need a pressure of the order of 10 to minus 9 torr, T-O-R-R. In the ordinary barometers that measure the air pressure, the measuring pressure in the range of, say, 1 to 100 psi pound per square inch, 1 to 110 psi. You can have a device that can measure in that range. An automobile pressure ranges from, say, 1 to 55, but 1 psi is extremely high in the physics we are talking about. We need residual pressure very close to absolute zero. So how do you do that? In this paragraph, the author discusses the method of exhaustion of the space between the flask and the bulb. So instead of attempting to measure the residual pressure, what he is going to do, he is going to follow the method of condensation and evaporation. So he's going to use two things in that method to get rid of all the air in the medium. He is going to use them simultaneously. The first thing, he is going to expose the entire device into a temperature of 400 centigrade. While he is heating the entire apparatus, he is continuing to pump, to exhaust the system by the pump. So he's using two things at the same time. One thing is heating the entire system, the other thing is suctioning the air out. While he is heating, he is going to use the charcoal to absorb all the vapor from the system. So the experiment will be as simple as that. He's going to use charcoal in one tube and another tube. He's going to heat the entire system using nickel or electric wires, like asbestos around each one of those with electric nickel wires, and he is going to put each one of these in a tube furnace. The heat is going to make the air inside the entire system extremely hot, while at the same time he is doing suction by a mechanical pump to evacuate the bulk of the air, and a fusion pump or a mercury pump to evacuate far below what the mechanical pump can do. He is going to keep the entire system under very high temperature, 400 degrees, while doing the suctioning or the pumping out of air before he is going to seal the system. First, so how do you know that you have extreme deep vacuum? You don't have any meter here. He is going to use a tube that not as a gauge, but to see the spark or the light inside it that can show up in the case of having any gas system. So the purpose of the heat is to remove water and any volatile substance while exhausting the system with mercury pump. How do you heat it? He is going to use nickel wire insulated with asbestos sheet wound by nickel wire. The charcoal will absorb all the hot vapors and the volatile material. Charcoal is in the tubes A and B, in the tube A and C. The first problem he runs into, as soon as the pumping ceases, as soon as you stop pumping out the air, hydrogen and the carbon monoxide line. Lines mean light, or the spectrum of the hydrogen and the carbon monoxide will start showing in the tube D. Tube D is a tube that is tube D. It is used as an indication of the vacuum, how deep the vacuum. If you have any lightning here, any source of light in that tube, means you still have gases that are sparking because the temperature very high. These two tubes will be doing the absorption of any particles in the air. These two pumps will try to remove every particle, vapor, or any material in the entire system. First problem, contamination will come from where? Of course, the air will be removed from the mechanical pump. The first contamination comes from the mercury. This is number one. The mercury used in the fusion pump to get to very deep vacuum. Of course, you have air can leak out, and you have mercury. You have a third problem here, the rubber tap that you are using to seal the system. You are going to have particles of the rubber. Of course, you are going to have water and other material, because the charcoal is just wood that is heated in vacuum at very high temperature. As soon as you stop pumping the air out, the air will leak inside, interact with the charcoal, and it's going to create carbon monoxide and hydrogen. How do you avoid that problem? That the hydrogen and carbon monoxide start appearing in the system as soon as you stop pumping air out. He's going to use another trick. So the first trick he is using here is heating and mechanical pumping of the air out. The second trick he is going to use dried nitrogen, pumping on the entire system and evacuating again on the hope that he can get rid of all the water vapor. So the second trick he's going to use a U-tube cooled in liquid air. Liquid air means almost nitrogen. Why do you cool the U-tube? You cool it to condense. This is the U-tube he's going to use to condense everything that can go through that U-tube. Air, water, any particles that were not absorbed in the charcoal. When you keep this tube extremely cold, you can prevent the air, the water, the vapor from evaporating again or volatilizing again and filling the system. So the trick here is very simple. You heat the entire system, you do the suctioning, you keep the charcoal hot, and as soon as you reach extreme vacuum by looking at the D tube, there is no sparking in it, you start cooling the U tube by liquid air and removing the furnaces and try to see how long can you sustain the vacuum. The condensation of the vapor of mercury and the tap grease, the grease that is in the tap that is sealing the system, and the charcoal in A and C. Everything that can pass through this is going to be cooled in U tube and kept in liquid air, extremely cold temperature, to prevent it from returning to the system. Another way to reach deep vacuum, you would have to depend solely on heating, condensation, and suction. How long can that last? He discusses also how the charcoal is prepared. The charcoal was made from fresh coconut, heated to 450 degrees in vacuum until gas no longer evolves. You keep heating the wood or the coconut until you have no more gas. Then you start the experiment of preparation. Say the problem here is that the coconut, because its hydrocarbons can be easily volatilized and decomposed. That is why it requires a lot of patience and a very thorough preparation. When that happens, when the charcoal is heated enough, suction is sufficient enough, he is going to close first the wide Y bypass. He is going to close this bypass as soon as the temperature here is 450 degrees and there are no gases evolving, there is no lighting here, everything is hot. He is going to close here before start cooling. Then after 5 hours pumping, tab T will be closed. That is next step. The first step was closing the bypass Y. After 5 hours, he is going to close the tab T. Once he closes the tab T, the system is closed. The pumping have to stop. When you close the tab T, you have to cool C in liquid air. So after you shut down the system closed here, and you shut down that, you sealed that early, you have to remove that from the heater and start cooling with liquid air to condense and trap the particles that are absorbed on the charcoal in C. You need another 5 hours before you finally close X and quickly remove the furnaces. Let us see how tedious the experiment is. The entire system is heated at 400 degrees. The charcoal is heated at 450 degrees until there is no more gas evolving from the charcoal and there is no lights in D. Once that happens, you close or seal the bypass Y. After 5 hours, you close the tab T and cool C in liquid air. When you cool C in liquid air, you are now closed here. The reason that you're cooling C is because that is closed, that is closed. So what is open? You allow now everything that's hot to be absorbed on the charcoal. After another 5 hours, that will be another 5 hours, you close the bypass X and you cool A in liquid nitrogen and you keep A cold all the time. As soon as you pass the 10 hours, that portion of the experiment is already sealed out. Your only hope is that you can keep A cooled in liquid nitrogen all the time to prevent losing the vacuum in the system. The process of exhaustion or evacuation of the air will take 24 hours. Imagine how tedious that process. 24 hours to get ready to remove all the particles such that to avoid the discharge in the tube. So why are we taking all these troubles? The troubles of how to remove all the air out of here, all the water vapor, and seal it. You are going to seal it here, you are going to seal it here, you are going to seal it here, you are going to cool here, and you are going to cool here. First, you are going to heat the entire system. Why do we have to do all that? We have to do all that because you need that space between that bulb and the flask. This is a magnified drawing. You need the space between the bulb that contains the radium and the flask that contains the bulb to have nothing whatsoever, no water, no air, nothing. If you can do that, you are going to keep the charge on the bulb and the charge on the flask without sparking between them. If you have a spark, meaning you have discharge, you cannot you cannot measure the voltage on the bulb. The voltage that generates because of the radium inside that emits beta particles which are negative will become a positive, which means this bulb will become positive. Means electrically positive. If it is positive, you do not want any air around it to avoid any spark. If you get rid of all the air, you start measuring the deflection of the disk E. Disk will go out. How do you measure it? By a microscope. There is a microscope from the side. You look at it, you have certain kind of marking. You can measure how far can that disk go down or go up. In this paragraph, the author will explain what happens after you evacuate the system completely from air, moisture, any kind of gases. Remember something, we are evacuating everything around the bulb. Everything here is evacuated and that will be sealed, that will be sealed, that will be sealed, and everything else should be evacuated. You might ask yourself, what happened inside? This is the bulb B. This is right here. This is the bulb. What happened inside this bulb? This bulb is sealed from the beginning, before everything, when it was filled by radium. And this bulb will have 3 dimensions. The first one was 9 millimeter in diameter. The second one was 1 centimeter or 10 millimeter in diameter. And the last experiment was 50 millimeter in diameter, 5 centimeters. So the author used 3 bulbs, different thickness, different dimension, but the bulb B that contains the radioactive material sealed, evacuated, sealed and filled with radium, or evacuated, filled with radium, and sealed from the beginning before we start evacuating the bigger flask and system. As soon as the evacuation is complete and as soon as the apparatus has time to cool, with the charcoal was cooled, it was heated to get rid of all the gases. Then it was evacuated by removing of the air and moisture. Then it was sealed and closed. What happened after that? You start seeing an abrupt discharge every few minutes. where is the discharge happening? Happening in the bulb that contains the radium. The question is, why didn't we see discharge before? You did not see discharge before because the system has air in it. When you have air around, this bulb in the flask, that air will glue all the time. You are not going to see anything inside the little bulb. That is the whole reason why you have to evacuate that entire space, have to be completely evacuated from anything in order for you to see what is happening inside that bulb. What is happening inside that bulb was that abrupt discharge every few minutes, and the disk of the electrometer will be displaced. Why it was displaced? Because you removed the air, the radiation creates beta particles, beta charge, or loses negative charge, so the bulb become positive, and the disk will gain some positive charge. The disk of the electrometer will become positive, start to move, showing that this is a very important comment. This is a historic comment now. The bulb was very highly charged. This is a very serious statement about the hidden force of nature, the atomic nature of energy. Once you move the entire air, evacuate, discover that radiation has enormous energy. And the bulb was highly discharged, then suddenly flew back. What flew back is the disk. So the disk is first the disk is charged by positive charge. It was displaced and attracted to the bulb. Then it loses the charge, it bounces back to the original position. Why? Because it seems like the charge leaks away. He is going to explain the reason that there is fluctuation. So first the disk is displaced, then the disk go back to the original position. During that time, in a dark room, remember, the room has to be dark for you to see what's happening. A yellowish-green flash, there is a flash, was seen to light up the bulb. Only the bulb has a yellowish-green flash. Why? Because there is some kind of acceleration and emission of radiation inside the bulb, not outside the bulb. While the interior, everything in the flask was dark. Remember, this is exactly the purpose of the experiment. The purpose of the experiment is to remove everything around the bulb, everything here, in order to see what is happening inside this bulb. As soon as you evacuate the system, this bulb starts flashing yellowish-green light, and the disk will be attracted. Why would the disk be attracted? Because this will become positive all over the bulb. How is it positive? Remember, we covered everything from inside with silver. So the flask is covered from inside with a silver layer, and that bulb is covered outside with a silver layer. So that silver layer will become charged positive because the emission of beta radiation. Beta is the negative electrons that are lost from the radium, and the radium will become positive. So what happened to the electrons? The electrons can go through any material, will diffuse through the silica and make the silica positive. That will electrify or induce a charge on the disk. So now everything become electrified. The disk will be attracted or displaced. Might be repelled, not attracted, repelled away. So there is a force. That force what makes you going to estimate how much energy does the radiation produces. So now you discovered the hidden force of nature by having flashes, having displacement of a disk. The magnitude of the displacement will tell you that the very highly charged bulb, the displacement of the disk immediately recommences, which means it goes and comes back. The disk is displaced, it goes back to its location. Why would the disk keep bouncing back and forth? He is going to explain that there is some kind of leak of energy, some kind of discharge happens in the air or through the silica. That discharge makes the disk loses the charge, then it charges again slowly. Mathematically, the force of attraction depends on the square of the attracting charge. Why? Because if you remember Coulomb's law says the force of attraction or repulsion is proportional to the square of the charge divided by the square of the distance with some constant of proportionality. So the force of attraction depends on the square of the attracting charge. Then at an ever increasing rate, the displacement will become increase until it gets to a maximum, then it started to bounce back again. The disk then began to move more slowly. At times it would falter and fall back a little. Why would the disk move slowly? Seems like the losses of the charge are saturated, or the leaking is maximum and the disk start to moving very slowly. The conclusion of the author is that the reason that bouncing happened is because there is a slight discharge were taking place. He's going to try to figure out where does the discharge happen. Finally, without warning, came complete discharge, which means the disk first is displaced, then it goes back to its original location. Then it moves back slowly, displaced slowly. Then there is a complete discharge, which means there is a break in the system, whether it's ionization or gases, or a break in the tolerance of the silver and the glass to tolerate the extreme high energy. Then he said that the cycle of bouncing back and forth was erratic. Erratic means unpredictable. Here he is going to explain why the cycle of the bouncing disk was erratic. He said it was expected depending on the quantity of the radium, the active material. How much radium did you put inside the tube? Because the quantity of the radium will determine the quantity of the radiation, of the beta radiation. The capacity of the system, which means how big is the bulb. So these two things, the quantity of radiation and the capacity and the volume of the bulb, will determine the cycle of bouncing back and forth of the disk and the discharge. The thin disk, if not in metallic connection with the flask, gained a free positive charge. He explains now why would the disk is displaced. The disk will be electrified by induction of a charge. The bulb is positive, will induce charge on the disk. There will be attraction. Let us forget now about the repulsion or attraction. There will be a force. We call it attraction because you have a condenser arrangement. The only problem he has now, because the disk become charged and the flask is covered by silver, so the disk is going to lean to be attracted to the surface. He is going to overcome this difficulty by tilting the apparatus to keep the disk away from the flask. Let us look at the drawing again. Which means when that disk is charged by the positive charge and the wall of the glass is covered by silver, the disk can be attracted to this side or to this side. He overcomes that by tilting the apparatus such that he can keep that disk from touching the glass. The last segment of the paragraph, he said that the system or the bulb that contains the radium can be discharged at will. At will means if you want to make a spark, to release the charge, to make the bulb loses the charge, you can use powerful X-ray. What would the X-ray do? The X-ray will hit the flask, the silver flask, and will produce electrons. And the electrons will swarm inside the flask to the surface of the bulb and neutralize. That will create a discharge and the disk will go back to normal. And the author was very sure. He said, the necessary charge being doubtless, without any doubt, carried to the bulb by a swarm of electrons released from the surface of. In this paragraph, the author discusses the results from the 3 experiments that he did. He did an experiment on a bulb that has 9 millimeters diameter. Then he did an experiment on a bulb that has 1 centimeter diameter. Another experiment on a bulb that has 5 centimeter diameter. In the first experiment, he concluded that the bulb might have a potential of the order of 150,000 volts. That is an enormous voltage that you cannot generate in real life between 2 plates or 2 electrodes in a small place. 150,000 volts generated by the radium decay into beta particles. That is enormous power of nature. In the case of the 9 mm bulb, the bulb was made from quartz. As soon as the apparatus was exhausted, spark perforated the bulb. The bulb was very thin, so there was a perforation or a hole in the bulb. But the hole was very small, and the radiation or the radium emanation diffused and condensed on the charcoal. Remember, the charcoal was cooled by liquid air in order to retain all the particles, the air, the water, whatever. The bulb that is 9 mm in radius was very thin. It was perforated, but he calculated the perforation of the order of almost 1/10,000 of a millimeter. That is under a micro. That is 1/10 of a micrometer. How did he get this figure? The rate of diffusion from that hole. Despite the perforation, he still believed the voltage was of the same order, 150,000 volts, stayed almost constant despite the perforation. When he used the glass bulb of 1 centimeter, there was no perforation. The glass was strong enough to maintain the radium without spark. In the case of 1 centimeter diameter glass, the author used platinum wire between the bulb that contains the radium and the rod, the silica rod that holds the radium in place. That way, the silica rod and the bulb were connected by a platinum wire. That way, he will prevent a spark from jumping in the air between the bulb and the flask. He wants to dump the bulb, the extra. If a spark would have to happen, if the charge was extreme, and the glass cannot stand the high voltage, the spark will leak into the platinum wire into the silica rod. He still believes that the potential at which charge cannot be prevented is of the order of 1.5 times or 170,000 volts or 170 kilovolts. That's compared to 150 volts that is produced before the spark develops. The author also makes the observation that the discharge potential or the voltage at which a spark occurs, that voltage decreases as soon as the charcoal is heated. As long as you keep the charcoal cooled, it will retain the gases, the fluid, the water in the tube that have the charcoal. Once that charcoal is heated to the room temperature, everything will start sparking. Sparking means charge potential will decrease. If you wanted to have the spark not happening until 150,000 volts, you would have to keep the charcoal cooled in liquid air. From this observation, the author concluded that the sudden discharge, which always limited the potential, took place through the residual gas. Of course, there are two sources or two reasons for a discharge to occur or for a spark to occur. Either you have a residual gas that ionizes and creates charge, or you have some leak in the supporting silica rod or the inability of silica rod to withstand the extreme high voltage. In this case, the author believes that charcoal, when it was kept under liquid air, he was able to conduct the experiment without having a spark up to 150,000 volts. There is another observation the author makes, that the slow and irregular rate of charging at high potential may have been in part due to conduction along the silica. He thinks the silica was the source of leak of charge that makes it hard to isolate the bulb from the flask. In either case, the author believes that 160,000 volts were sufficient to stop or turn back any particles emitted with a velocity less than 0.65 speed of light. Remember, the speed of light 3 times 10 to the power 10 centimeter per second. 0.65 of that is still enormous. At that speed, that particle can be stopped completely with a voltage of the order of 160,000 volts. You cannot obtain that in the laboratory, but you can obtain that by using the vacuum glass bulbs, extreme vacuum, and measure the induction of the force between the glass bulb and the electrometer. Here the author tried to explain why there is a limiting voltage for you cannot attain extremely high voltage. Everything has a limit, and the limit in the author's opinion was 160,000 volts before the spark can occur. Here the author explains or complains that experiment on discharge in vacuum were not very well known. Thus, discharge occurs because of ionization between residual molecules or particles of gas in the medium, or because of a limit on the insulating material. In this case, the author will mention few experiments using parallel plates. This author, the plates have about 0.4 millimeter apart. The author was able to keep high potential, if you have two plates, two electrodes, and the distance between them 0.4 millimeter. That is how much field you can maintain without a spark. The highest potential on that experiment was about 12,000 volts. Because the two plates were very close to each other, only 0.4 millimeter, and you can keep that kind of volts between them, the author claims here that the ionization of gas cannot justify that limiting spark because the space is very small and it shouldn't have sufficient gas collision. In another way, you can maintain 12 kilovolts and two parallel plates with the distance between them only 4 millimeter, 0.4 millimeter, very small. In this case, you can exclude the phenomena of ordinary ionization by collision in gas. That cannot explain the occurrence of. Here the author is very confident that he took enormous care in removing any gas from his experiment and that the ordinary ionization by collision was out of the question. Another way, the author thinks that the reason he has a limiting maximal voltage was because of the inability of the silica to withstand the high voltage. In the case of the bulb that has 9 millimeter diameter that was charged up to 150,000 volts, the force at the surface, the electric force at the surface of the electrometer or the bulb was 330 kilovolts per centimeter. The author claims that using pointed electrodes, the platinum electrodes, promoted discharge at much higher potential than between parallel plates at the same distance. Another way, if you have two flat parallel surface, two electrodes, and you have two pointed electrodes at the same distance between them, that distance is the same like this, that the pointed electrodes will promote discharge at very high potential. Of course, the author struggles with the cause of discharge in vacuum, whether the discharge is due to collision by ionization of the gas or because of the material, the pointed nature of the electrode, or because of the nature of the material itself. So the main issues here, why can't you maintain or attain very high voltage in vacuum? Is it the introduction of air or the spark gap? What is limiting the value of the electric force? Those are the issues that the author struggles with in his experiment. In summary, the author believes that the maximal force that can be measured in the order of 1 million or to 10 million volt per centimeter, and in other cases was about 10 million volts per centimeter. That is the force produced by the accumulation of charges from beta particles on the surface of the glass bulb. Because of that, because of the struggle whether the discharge was due to air or due to pointed material, the author is going to start another experiment by increasing the size of the bulb to 50 millimeter. 50 millimeter means 5 centimeter. He is going to separate the bulb surface from the flask surface, since he is good in evacuating using the heating process, the heating the charcoal and the entire system, and the diffusion pump and the acute deep cooling of the charcoal. He is confident that 50 millimeter bulb might solve the problem of discharge, low pressure, at low potential. This third experiment, the bulb is now 5 centimeter in diameter. Electrometer spring is much stronger, so it can stand much greater force attraction because the bulb, the gas bulb is going to be large. You expect it to have greater force, so he needed a stronger silica spring. Now he increased the capacity of the system, increasing the diameter of the bulb. And the observation here was interesting. When he increased the diameter of the bulb was charged to a constant potential. That potential can be discharged by the trick of using X-ray for at least 3 weeks. That is enormous accomplishment to be able to retain extremely high charge, extremely high voltage on a glass bulb for 3 weeks is a great accomplishment. The accomplishment was due to the perseverance of the experimentalist that he discovered that a 50 millimeter diameter glass bulb was the interesting exquisite technique he used to evacuate the system and retain the impurities and the gases cooled charcoal that achieved that outstanding result of maintaining high charge on a glass bulb for 3 weeks. During that time, the potential gradually rose. How far can you get a potential for 3 weeks? Rose to about 100,000 volt or 100 kilovolt to 11 to 110 kilovolts, while the current, the electric current that can be carried away about 10 to the minus 11 to the power minus 11 ampere, very small current. We are talking about now a microscopic part, subatomic part. In these 2 weeks, the current dropped a little, about 2%, because of the radium loses by decay. Therefore, the current will drop. But 2 weeks or 3 weeks least of retention of charge is an outstanding accomplishment. In this case, the author observed something else, that the temperature of the charcoal did not reduce the potential, the voltage on the bulb, and that the leak occurs only, without any doubt, along the silica support. Of course, in this case, when at the 5 centimeter bulb, the support was stouter and less scrupulously cleaned, because it was cleaned enough. In other ways, the author concludes that the conduction of charge of current through the silica limited the potential, the voltage, the maximum voltage on the bulb. And that conduction, because it reduced the maximal potential, it also prevented the spark. When you prevent the spark, you will able to maintain the charge for 3 weeks. By the end of his article, the author concludes that silica was the source of conduction, but that reduced the spark. But having sufficiently thick and large glass bulb with sufficiently large amount of radium, he was able to maintain a reliable experiment. The main difficulty is the lengthy process of exhausting, the lengthy process of evacuation of air. Now the author accomplished his goal, finding out emission of beta radiation, charged or created a charge of a potential. That charge caused a potential difference of 150,000 volts were involved in the expulsion of beta particles, electrons. Another way, the author wanted to stress that the energy of expulsion of the electrons or the beta particles from the atom was enormously high, up to the 150,000 volts. At the end, the author, Henry Moseley, thanks Professor Rutherford. Remember, Professor Rutherford's school, experimental physics, that depends heavily on classical mathematics to analyze experimental results and experimental settings in very great details. But in this case, the author did not tell you how did he calculated the figure of 150,000 volts, because there is nothing in this note that can tell you how this author calibrated the silica springs. As you see in this case, the author measures the voltage through the deflection of the silica spring observed by the microscope. How did he get to the figure of 150 kilovolts as potential involved in the expulsion of beta radiation? We don't know in this article, but we can know when you follow the work of Rutherford, when he discovered that the nucleus was the center of the atom.